Dr. Tong is the president of the consulting firm based in Seattle. Got his PhD in University of Washington, I think it's 25 or 30 years ago. And not only he's a very experienced transportation planning modeler, but is actually a computer science genius. He wrote the entire GUI himself. Very good at all kind of programming. I think this GUI is written in C++ and Java. And Python. 1 year ago, he got a project from Federal Highway to actually experiment plugging in DTA into a 4-step model, which is a PSRC network he's working on, the Puget Sound network up in Seattle. And then took the opportunity, he started to kind of customize his GUI to become, actually it took me a while to convince him. I actually took his GUI to be able to seamlessly integrate with DNST. And so this what you in front of you right now is something he actually spent an entire year to customize. But this GUI is really built upon his 20 years of development of the GUI. So all these are very exciting development that I've been seeing, and particularly for me personally, work on DNST for so many years, and this is the first time I'm able to kind of unleash the power of DNST. I'm able to see a lot of information from DNST myself. So this GUI become my latest toy that I play all the time. Robert, you want to say a few words to everybody?
Yes, I think Dr. Chu also has a very good product, the DNST, but because it's lack of advanced GUI, so it's kind of hindered many project applications to be able to use that tool efficiently. Yeah, Dr. Chu, I believe the DNST has probably one of the best DTA algorithm out there. So I'm just happy to add this GUI to his DNST DTA engine. So the combination of both, I believe, will make the DTA work applications much easier. So yeah, right now we are testing different size of a network, and the Nctcog is currently the largest network we are testing. I think the performance is still very, very good, though there still needs some improvements, and Dr. Chu also is working hard to make sure DNST can do large network very efficiently. And on the GUI side, I think I'm also able to display a large network very efficiently. So just wait and see. There's a new tool on the block. Okay, back to you.
All right, thank you, Robert. So I basically know most of you for years, and in TTI side, I have quite a collaboration with TTI. TTI has quite a few engineers who has been using DNST. I know Bruce and Raj for several years, and also had the understanding of there actually has been very proactive and pioneering that they started testing DTA, actually ahead of a lot of agencies a few years back. So I think they have a lot of background information and knowledge to be able to challenge DTA developer as well, to be able to appreciate any potential benefit from a DTA model. So the background of this effort is a few months back I paid a visit to Nctcog, and I took the opportunity to explain the basic concept of DNST. All sound great on paper, on presentations, but I took a challenge and told them, hey, give me the Nctcog network. I know it's gigantic, but I think DNST can do it. So Baruch offered the Transcan model. And then of course we sort of it's because it's kind of our side job, so we kind of work on this on and off a little bit. But really, we got a lot of help from Robert to be able to actually bring everything to Dana Studio, because we want to show you the best of the combination of Dynasty and Dana Studio. So here is the network in front of you. Obviously, I'm still one of the users still learning Dana Studio, but Robert definitely can give you a lot of more detailed information about the GUI itself. But in a nutshell, Dana Studio is a GIS-based system. You start off by importing the shapefile, preserve all the let-long informations. All the information are stored in the internal databases, so it's very compact. And also means that because the internal database formats, it's very flexible for you to work with the data, because with SQL languages, you can do a lot of query, a lot of systematic operations very, very efficiently. And then the way it works is Dana Studio is a separate entity with Dynasty. When you hit the run button, basically, assuming you have everything prepared, you want to run Dynasty, you hit the button, you generate Dynasty data formats, and then run Dynasty, and then after it's done, you bring the simulation output back to Dana Studio for display. And so that's how it is being structured. It's kind of a loose couple between the two, but that gives me a lot of flexibility in updating the simulation engine as well as updating the GUI. We both can move in parallel. So I just want to show you something very basic. You can see that this is the network itself, not much different from what you have been seeing in the past in the turbo demand model. You can see that zoom in, zoom out is fairly flexible. Again, and this is the main windows. On the left-hand side, you have all the layers. So everything is by layer. You can turn layers on and off. And this is a different layer. I just turn on, link one layer. I think I can also turn on boundary layer. That's all the zone information that we have. You can on every layer you right click, you have a lot of options you can choose from. If I right click on L type, I can change all the colors that you can display. I can turn on a street layer. If you have a street information, definitely you can show all that. And a lot of this information are originally from the Transcat file, and then Robert is able to pretty much bring everything into it. And most importantly, you can also see all the signals. Robert's import process has a fairly clever way of importing the signals, and then what I noticed is, and Robert, you can elaborate that a little bit, is we do have quite a bit on signalized intersections. So some of them are stop signs, some of them are signals, and so we are able to actually bring your signalized intersection and unsignalized intersection into the model. And this is also very important for testing as well, because you can really quickly check, where, again, this is initial conversion, and Robert and I didn't really spend a lot of time cleaning it, but if you imagine, want to clean the network, you can very quickly just spot check on the network to make sure the signal is being located in the right place. If you want to modify the result, click on that. It's going to tell you what's the control type. If you want to change it, right click on every field, you can change the value. So it's very, very convenient. So there are a lot of editing, basically network editing, network attribute. You can even add node, add links. There are a lot of features allow you to actually edit the network if needed. So I will not go through all that details, but really just kind of highlight the results of this example. So I just turn off the control. Before I turn on the control, I probably also want to show you the generation link information. We know in the 12.33 model we have a centroid and we have a centroid connectors. That's the load of traffic to links, but it also try to maintain some consistency with your 12.33 model. So, for example, this is sort of kind of centroid. These are all the connectors that actually feed the traffic to. So this kind of allow you to visualize where do your where do your traffic loaded is loaded. Is it being loaded in the right way or it's been loaded incorrectly? You can quickly visualize that. The number on each connector is represent the loading weight. You can specify, you can control amount of traffic you want to load to the network, and which is not something you can do in your travel demand model, but you can control for all the traffic coming out of that zone, how many percent go to this link, how many percent go to different links. So you have the flexibility to control that. I just want to point out that's the main differences in terms of DAS-T, which loads traffic on links and randomly assign vehicle on the link instead of coming out of connector. Okay, so assuming you have everything cleaned up and you are ready to run it, a nice thing about that studio is something I want to mention is it has a scenario manager. You can set multiple scenarios, and the scenario is very useful in the sense that it duplicates minimum amount of information. In the old day, if I want to run 5 scenarios, I need to copy 5 folders, and everything is duplicated 5 times. In our case, a lot of time we have the same domain information, but our different scenario maybe differ in the network situations. That you have different construction strategies, you have different pricing strategies, so you can set up different scenarios, and the scenario allows you basically just duplicate the least amount of data. Later on, I will show you. I can show you using this network yet, but I can use another network to show you the scenario comparison, how powerful the scenario comparison could be later on when you have multiple scenarios. So this is something I want to point out about the scenario management. Before I move on to a result, I want to point out the Python editor. What I like about this GUI a lot is it has a Python manager. I personally and my team writes a lot of Python script. The simulation input-output may not necessarily to our most suitable to specific projects and require some customizations. And this Python manager allows us to write our own script, and actually we can manage all the Python script directly from here. So really the possibility is endless. You can do a lot of things you want using this Python script and a manager. And of course there are a lot of data table editor. There are a lot of information you can use to manage your data. Calc is a very nice feature where you can see these are the data in the node table fields, and you can use all the built-in function to do a calculation of database attributes for all the fields that you are interested, and you can populate a result very, very quickly. So here I have a lot of field: distance, street, link types. I have a lot of information about link. I can use this kind of basic logical Boolean operation condition to quickly manipulate my results. So that's a very, very nice feature we have. So I will not go through all that. Let me just kind of. Any question at this point? Up to this point?
The slide, the part that you show the percentages that come out of each centroid connector to the links. Can you set so that the assignment decides who comes out of where instead of forcing what percentage comes off of what connector and goes on what link? Or that's always the input? You have to decide what percentage of the zone traffic what link?
Actually, user doesn't need to worry about that. You know, the assignment will determine that. But the added benefit is you do have a opportunity or flexibility to override it if you need to. For example, there's a square, particularly later on when say we deal with more operation type of issues. Like a shopping mall. Shopping mall usually have a few entrance exit point. So you know, okay, most of the traffic are in and out of specific link. And you know those area has those link has much more volume, much more loading than those link in the back of the mall. Mm-hmm. So we found that could be very important if you're doing some sort of more operation type of analysis. Now you may be wondering why should I worry about that kind of level of details? Now the benefit of Dynasty, a lot of agencies use this for is that they carve out a sub area after they've done a regional model. Then they keep it, and if there's a corridor study, then the member agencies or a consultant walk in and request a sub-area model for a corridor study, then there's a way for us to actually create a sub-area, and the network as well as the demand through that sub-area will be preserved, and you can take that and send it to a consultant for them to work on, and so at that level, at the corridor study level, the ability to customize or be able to control the loading become important.
Now, all those center connectors are generated automatically?
No, you define it.
Okay. Let me add a few things here. Well, initially, when we convert from travel demand model to Dynasty, we just use your current central connectors as a reference. So all the connectors to the adjacent links will be used as a generation links. Then the loading factor is based on the total lane miles on those adjacent links to calculate the percentage. So those are the defaults initially. So after the initial conversion, if the user can override these factors based on your land use pattern or your local knowledge. For example, you know exactly where are the driveways, where are the shopping center, where are the major trip generators. But in the typical travel demand model, we probably don't pay too much attention on those loading points. But when you do this DTA, and those loading points may become important because you don't want to load too much traffic or at a certain link on certain links that will create arbitrary bottlenecks. So this is kind of a work during the calibration, validation of the model. This kind of adjustment will need to be done.
Oh, correct. Actually, we do care for the location of center connectors, especially when they do corridor studies. They go in, and if something doesn't make sense, they fix it. Yes, and we also have certain rules that, like, you can't cross links when you draw center connectors, or you can't cross freeways, or you can't go across rail lines. But I see here that our connectors are connected to everywhere. Is there a way that you can limit what is created?
Yes, you can certainly you can modify the script and to just customize. If you know your certain rule, okay, we can this conversion tool can be tailored to your local needs. Yeah.
Thank you.
Yeah, right now we just pick up whatever the central connector you have existing in the existing model. Yeah.
Okay, great. Yeah, as I mentioned earlier, we literally didn't spend any time cleaning up the model. So this is the to make it operational, definitely need a little bit more checking and examination. Okay. Okay, so the scenario I was running, I can show you this real quick. I was just running a 3-hour simulation. This is actually a 20 iteration run I did But as I finished, I ran another one shot just for for different purposes. But the DTA I ran over was 20 iterations. You had different way of loading your OD, your domain. You can load OD matrix. You can load vehicle path file, and OD domain matrix is usually we use for set out a baseline case. We prepare OD table, then we run with it. Now, there's advantage of using vehicle path file, particularly for the scenario comparison. Now, if you want to compare your baseline case against other 3, 5 scenarios, you want to make sure everybody's been loaded with a vehicle path file, basically the same population that generated from the initial OD run. So you strictly control the origin, destination, departure time of all those vehicles. And that's one way to greatly reduce the random error. And so the difference you see between baseline and the scenario truly reflect the impact of the scenario itself. And that's why, but there's a model in detail, so we can discuss it later. So these are typical window you see when you specify how long you want to run it, how many iterations you want to run, what's the demand loading mode. And when you hit the run, and then you start preparing the data set, and then in a few seconds, Dynasty starts, and Dynasty take however long it needs to run until it finishes. The result will be brought back into the GUI. So in the next few minutes, I'll just kind of show you some of the basic information for this very simple case. First of all, you want to kind of check on number 3. This is called system departure time and travel time profile diagram. So I just uncheck everything. You can see that in this demand, what I did is very, very simple. I took a 2-hour demand. I just did a uniform distribution. So you can see that in these 2 hours, the demand is very, very uniform. Definitely, this is not going to be the case in the real case. On top of that, I kind of tell you it generated 4.5 million vehicles in these 2 hours. And at the end of 2 hours, the 3-hour simulation, so I generate demand for 2 hours, I simulate 3 hours. There's still 500,000 still in the network. They have not finished the trip yet. If I run longer, all these people will get out of the network. Average trip time for all these people are 45 minutes. That's actually fairly, I think it's because this network is a little bit larger. And the average delay is about 5 minutes. So departure curve is flat, and then arrival curve is pretty normal. You have 0 arrival, and then it's gradually to increase and reach some sort of steady state. And then and the delay is right here in terms of minutes, and the amount of unfinished trip. And then you can do a lot of selection. You can select based on different departure zone, the vehicle type, and vehicle classes. You can do just a very simple high-level query of your general information about this particular run.
So this is the AM demand, AM peak demand, 2.5 hour demand.
Right, this is 2.5 hour demand.
Yeah.
And then of course then you can do an animated. This is a fun part of that. You can refresh speed. You can change to default, or you can change to 5 minutes. Band size, you can increase the band size a little bit. Here is going to show you basically the volume plot diagram you used to see in your travel model. But the beauty of that, you can see the dynamic progression of the volume coming out. These are external zones. You can see the volume start coming from outside, and this is kind of give you a sense of progression of your traffic. And when I do 5 minutes, probably it jumped too fast. I can replay. I can just change to default, and I can replay the diagram. So right there you can see that the traffic was growing from gradually, and then those area, particularly in the North Dallas area, are definitely higher volume. Looks like that's because there are a lot of more developments in those areas. And these are Route 635, and then these are the US 75. These are all the major corridor between Dallas and the Fort Worth. If I zoom in a little bit more. And of course, you can change the bandwidth too. You can change the bandwidth depending on how much you want to show. So this is the bandwidth plot we used to see, but now I'll be able to see in dynamic fashion is kind of neat. And see how it's changing over time.
Can you also talk a little bit about how much disk space you require to save the path, to save all the information you need to show it on the screen?
How much space?
How much disk space? Yes.
Oh, disk space.
The file size.
Yeah, let's check it out. So these are all the files. That will be for this scenario. If I right click on this, 12.8 gig.
Yeah, the trajectory file is quite large.
Yeah, most of it is the trajectory, yes.
Right. And you can see that this is direct output from DST, vehicle trajectory 2.2 gig. These are demand file. Okay, these are demand file for DST. These are largest one. And anything with BO4, these are the internal files that are used by Data Studio. But you can see the largest one are the raw data from DST.
So Yi-Chang, this is Arash. Can you remind me of the algorithm and is it a user equilibrium, dynamic user equilibrium?
Yes.
Like every 5 minutes, or what was it? I don't remember what it was, that the logic that you used.
Oh yeah, this is a very standard DUE. So the result I'm showing is after 20 iterations. This is after the assignment. For 20 iteration and equilibrates. Vehicle are right here. Aggregation intervals. So every 15 minutes, vehicle departing at every 15 minutes, we find the best time experience travel time dependent shortest path for a vehicle departing at 15 minutes.
So so let me make sure I understand. So that means every 15 minutes they reach to equilibrium. Is that what you mean?
So keep in mind, this is, you can say that, okay, but this is not taking time slices. This is not taking time slices of demand and run a static assignment within that 15 minutes. This is saying, okay, so we have to first differentiate this from static assignment, time slicing static assignment. The time slicing static assignment is saying every 15 minutes I'm running a static assignment, but you also assume that vehicle would depart and then arrive at destination within that 15 minutes, which is not realistic, particularly for this kind of network. Vehicle may take 30 minutes to travel. So the true DOE is saying that vehicle departing the same 15 minutes, if they go to the same origin and destination pair, they will arrive at the same time. And the same time could be 30 minutes later. It will be 40 minutes later, but doesn't matter. If you leave at the same time, you take different routes, you all arrive at the same time.
Okay.
But that's a future time. That has to be a future time.
Yes, I understand that. But basically, what you're saying is that within the 15 minutes, so the demand span is 15 minutes, and within that, the same OD. Now, it may not reach the 15 minutes to the destination, but if you let the time go, it will reach at the same time to that point.
Exactly.
But you reach to that point with 20 iterations only, right?
So you have to iterate multiple iterations. When I say iteration, is actually you run simulation for the entire, say, 3 hours. Okay, yeah. And then you do assignment outside the simulation, and feed the assignment result back to simulation again. So this is called one iteration. So you can think about each iteration is 1 day. So it's 1 day of learning, 1 day of trial. And so 20 iteration means that actually we simulate 20 days. That people try this for 20 days and eventually reach the equilibrium.
So, well, let me see. I'm getting a little bit confused over here. So if you run the whole 2.5 hours, basically every time you run it for the whole simulation for all of it, but 20 times you do that, right? Is that what you're saying?
So let me do this real quick. So let's come back to this framework that we kind of talked about last time. Okay, so vehicle are being loaded every 15 minutes. Let's put it this way. Okay, actually vehicle loading every 6 seconds. Okay, so this is an entire 3-hour simulation. And vehicle have been loaded, and then vehicle loaded here may take 30 minutes to arrive to destination. Vehicle loaded here may take 45 minutes to get to destination. So simulation takes care of, you know, how long how they progress through the network get to their destinations. So imagine this is real life as you and me traveling. We leave at a certain time, we take certain route, and then we arrive at our office a certain time later. Now, so this is a kind of 1 day. And at the end of that simulation, we said, okay, certain users not happy with their route, so a subset of the user would get a new path and adjust their path. And then the next day, everybody, you know, would take their path and basically take their path and run again. Okay, so this process again, so that's another day. And then repeat again, another day. Repeat again, another day. Every time I go through one process, 1 day, I call one iteration.
Okay, and you start from free flow time, right?
I'm sorry?
And you start from free flow time, right?
No.
The network is empty.
Well, yeah, if you look at this, right, I mean, at the very beginning, it's free flowing, but this is first 15 minute, 30 minute, hour into simulation. Later, just in a few tens of minutes, network will become loaded.
Yes, I understand that. Yeah, so,
right.
So what is it that you guarantee in this? What is the convergence in this system?
So the convergence says, okay, for every OD pair, and if I leave at the same time, like for say, I used to live in Richardson, and if I go to downtown to work, okay, so everybody leave from my neighborhood, the same subdivisions, and go to downtown to work. Maybe 100 of us. We all take different routes. Let's say we take 5 routes. I guarantee that after the equilibrium process, all 5 of us, all 100 of us, although we take 5 routes, we ended up, arriving at the downtown at the same time. So the gap measures the differences in travel time for 100 of us. If all of us, if the travel time are very, very close, those 5 route travel time are very close, then the gap is small.
Okay, and if all of these 100 people leave at the same time, right?
Right. So if there's another 100 people leave at a different time, say 30 minutes later, I don't guarantee the travel time will be the same as those who leave 30 minutes earlier because network conditions is very different 30 minutes later.
Yes, and that's the dynamic part of this.
Right. But I do guarantee those who depart 30 minutes later, those 100 still experience the same travel time among themselves.
Okay. And in your setup you assign, you basically put the relative gap in this, right?
Right.
Okay. So this, now this doesn't this create an internal loop first, and you mentioned the external loop.
No, there's no internal loop. Internal is
okay. So it's all at the same time.
right. Internal is more like a simulation delta. Simulation is progressing. 6 second by 6 second. You can call it a loop, but it's really just a time steps. It's moving forward.
I see. Okay. So all right. So in this system, so you simulate the whole thing, and it is a kind of a simulation. So you have vehicles, right?
Mm-hmm.
All right. So it is a vehicle. So tell us how long did it take to run? You said 20 minutes. Is that what you said? No, you said 20 iterations. How long did it take to run for these 2.5 hours?
Right now I have not optimized it yet. I just run it. There are certain ways to optimize this. Right now it takes about 45 minutes to run one iteration.
Okay, so 20 times that 45 minutes?
15 hours, probably 15 hours.
Okay, that's not that bad. I was thinking it took even longer.
No, actually not bad at all. It's actually not bad at all. And then this, of course,
it's not bad.
And then the memory usage is about 8 gigabytes. The peak memory usage is about 8 gigabytes. So you can run it on any desktop computer nowadays.
8. This is the RAM you're talking about?
Yeah, the RAM. And most of the computer I buy now, they are minimum come with 16 or 24 gigabytes. So the memory is so cheap right now.
Oh yeah, that's right. That's not a big deal. Yeah, 15 hours is not that bad. It is manageable.
And as I said, this can be further optimized.
Yes. Yeah, we're not in that stage yet. Yeah, the fact that you could run it in this amount of time is very encouraging.
Yeah. Sounds good.
And what was the relative gap that you put over there?
The relative gap, we usually set to about 5%.
Say that again?
5%.
5%, okay.
Yeah, and keep in mind, DTA would never get to 10 to the minus 4 like a static assignment because the randomness in the traffic dynamics and the signals.
No, that's not. I don't know. This is something we got to learn. You probably know better than us about this, because this even 10 minus 4 may not guarantee anything in the DTA.
Right.
Maybe it's not an improvement because we're talking about what do we calibrate at the end? We calibrate volume and travel time, and we may achieve that to even 1%, or maybe 5%, maybe 10%.
That's right.
That's a different story. Yeah, so that's what part of the things that we don't know yet. What is it that actually should be there?
And when you ran the daily, you actually used the whole complete daily demand. Is that right?
Yes.
Okay.
So does it make a difference? I guess it makes a difference if you run daily, right? Than 2.5 hours AM, right?
Definitely. If you run daily, then you probably need you need more core. Right now, I'm using an 8-core machine, but you can buy a more powerful computer with more core because Dynasty is fully multi-threaded. So you can definitely take advantage of multiple cores.
Yeah, we can parallelize this and do some optimization of the code. But these times are not bad at all.
And I also found that using a solid-state drive will make a lot of difference.
Yes.
So basically, what we have not, but I'm going to try to test it, is to actually run this on a solid-state drive. That the I/O will cut down by a lot. And from people have been reported that runtime I/O solid-state compared with the typical drive is about 10 times. And so I anticipate could be another 20 to 30% improvement for me.
Okay, now let me ask you another thing. So you saved the trajectory, right?
Yeah.
So all of the 100 people that left from Richardson and went to downtown and took 5 paths, all of these 5 paths you keep. The last path that was equilibrated, you keep that, right?
I keep all the use paths, yes.
Okay, use path, yes. So if you do a sub-area analysis, the paths are used and you can give us a matrix quickly, right?
Exactly.
And we can take that to the market simulation and do it there. And probably works better than, it certainly works better than our static equilibrium.
Right, right. And
but it doesn't guarantee that it still works, right? Because still there are things that you didn't consider in the simulation.
what do you mean? I'm sorry. What do you mean that doesn't work?
Still there are things that they're not as accurate as in the market simulation as that they are here. So we may encounter queues that actually are longer than what we thought in the dynamic.
Oh yeah.
But this is a much more reliable approximation than before. This is a huge improvement. This is what we're looking for basically in this.
Okay, great, good to know. Good to know. Yes, I mean, for me, it's just kind of a lot of fun just to be able to see such a huge network be able to display dynamic information.
Yeah, I think this is great. Yeah, I mean what I mentioned about market simulation is only one of the applications. This by itself is an application itself, because there is a lot of things that can be analyzed in this.
Yep. I can also show you the way Robert designed his GUI is really have in mind as a planar. So you can see that it's kind of slack link analysis. For example, if I'm interested in traffic going through I-35, or maybe on this segment, I'll copy link number here and paste it here. And then it does say I want to do 2 hours. So you can see this is the slack link analysis.
Oh, I see. Okay.
Right. So you are pretty good at, very used to this slack link analysis. And beauty of that is actually, if I show table, you can actually see the route itself. You can actually track individual vehicle on this table, and to see where they are from, where they go to. The beauty of this is that, vehicle ID are unique. Later on, when you compare scenario, you can actually track the same vehicle ID and see how this particular vehicle is doing in a baseline case versus scenario. And you can tell a lot of good story about divergence, for example. Imagining this is a new freeway, for example, a new stretch you build, and you put a slack link analysis, you can tell a story about who actually used that stretch of freeway.
Yeah,
so,
yeah.
And then of course you can show by vehicle type. You can query by vehicle type. You can see I'm showing a truck. I'm showing a HOV. And I can show for all the vehicles. Okay, so this is a slack link analysis that's pretty useful.
Yeah, and it's very quick also. Yeah.
And it's also the GUI operates fairly quick. And then the fun part I like to play a lot is the one I was just showing you is the animation part. I can just show 1 minute. Refresh speed, I have different vehicles. I maybe just for me to show 1 hour for now. So this is actually displaying individual vehicles. So I can change color. I'm showing SOV is red, and then HOV green, and the truck is orange. I have too many warm color. I can change it to different color. The black is a stop and go vehicles, means that if a vehicle actually is experiencing congestions, you actually turn dynamically turn black. So some places you start to see some black colors later on. And this is good for local condition analysis, also for diagnostic. When you start setting up the model, if you see a lot of blob or black, that you probably you don't have a good maybe there's a problem in the coding of network. And actually we use that to a lot to actually find out some of the coding issue even in the original travel domain models. That could be very useful as well.
Yeah.
And then the typical technique we use is also to actually show trail, with delay, visual background. This is actually to show the delay information in the session in terms of circle. Let me actually make the symbol size very small. Make all this very light color. And so I can see some of the circle here start to show up. This is kind of give you a sense of where you see there's a lot of some congestion here start to show up. And this is also pretty useful for scenario comparison. You can compare baseline case with the scenario, and as a result of the scenario, you can see either congestion got alleviated or actually congestion got pushed to some other places. And circle itself is pretty visually effective in kind of tell the story.
Can you zoom more on one of these circles, around one of these circles?
These circles?
Yeah, can you zoom more Wood or Rogers?
As for example, this place.
This is amazing that you don't have to stop the simulation and zoom in. You can zoom in while the simulation is showing.
Yep. So you can see all this growing, right? You see the stop and go vehicle right here? Right? So basically, looks like timing is not enough for the vehicle here, so they start to queue up. And then this circle will start to grow as well. So you can see the circle is consistent with your simulation results. And here I just turn on the trail. Trail means that it doesn't refresh. If you turn off the trail, you refresh every second, right? When I turn on the trail, it just stays there, kind of use a way to let you see the progression of congestion.
Now, can you show a section of a freeway also with a very small interval, like 1 second? So basically, we can see the vehicles go one after another.
Oh, sure. You want me to turn off the trail, right?
Say that again.
Yeah, we don't need to see the trail. Just
Yeah, we don't need
individual
to see the trail.
vehicles.
Yeah, just individual vehicles.
Oh, sorry. I turn on the background. Let me stop this. I should turn off the background. Oh, sorry, let me turn off the no delay too. Sorry, I need to turn the color back. It's become a little bit too light.
Yeah, it's okay. Take your time.
I can make a little bit slower. Again, it's just getting started. You can see this is 8 minutes into simulation. I'm refreshing every 6 seconds. And you can see there are sometimes there's a blob here showing the vehicle start to climb together.
Can you move up this area a little bit so we can see the 35 and Buddha Roger when they reach each other? Okay, yeah, that's. And now zoom in. And now zoom in.
This is 35, right?
Yeah. Yes, that's right. Yeah.
You want to see? You want to stretch? Look at this stretch.
A little bit north of that. A little bit north of that when. No, that's good. That's good. The previous place was to show downtown.
Right.
This is basically the place that I'm looking for is just west of downtown.
Oh, I see. Here.
No, just downtown where the 35 and Buddha Roger. Buddha Roger is the one between 35 and 75.
Basically right there. Go up north and go, okay, stop right there. Oh, no, it's okay. The previous one was fine. Just zoom into downtown. That would be fine.
Right here?
Yeah, zoom more. Yeah, this is good. Zoom more. Yeah, where all of those ramps come together, that red road with red ramp. Yeah, because that's probably where the queue happens. I want to see some queue on the ramps.
Actually, the queue you saw here is because there's a stop sign right here.
Yeah, that one is on the frontage road. Yeah, let me see what happens to the freeway. Yeah, probably something is going to happen. Even though this is not calibrated, I understand that, but I want to say that something is going to mess up here.
Now, these arrows are individual vehicles. Is that correct?
Yep. Yeah, we're 20, still early, 27 into simulation, so.
Yeah, I think
Hey, Dr. Chu, this is Min.
I mean,
Just a quick question. Does the GUI have a built-in function that you can record some of this so that we could show it to others so that they don't have to have the software to see it, but they can we record it in a format that others could
I currently I'm recording our section today from GoToMeeting. So if you're interested, I can share with you the video. I just recording now.
Well, Dana still does not have the built-in the recorder, so you can buy a cheap third-party commercial software to record the video. Yeah.
Yeah, like a Camtasia is the one that we used to use.
Okay.
Maybe I can let it run a little bit fast.
Now, when you were showing the stats about the model run, you showed how many vehicles were generated, how many vehicles got to their destination, and how many vehicles did not get to their destination. Would you also know how many did not even enter the network?
Actually, that's a good question. We do have it, but Robert GUI is not showing that yet. But it's
okay. But you do know how many didn't even get the chance to enter.
Right.
Okay.
Okay, I see some queue here.
Yeah.
Keep in mind, I didn't even calibrate the traffic flow model. So if there's no congestion, maybe traffic is moving too fast.
Yeah, Yi-Chang, you probably need to show them how to display the traffic flow model, how to define the traffic flow model.
Oh yeah, that's something we can talk in a bit. I just want let Arash see if
Yeah, that's good. I think, yeah, some of these queues are forming. Yeah, and this model is not calibrated, so we can't really, but yeah, it's clear that the software shows some of them. And I think this is also development work. So, Robert, can you click on an arrow and actually follow it, show that it moves, so it goes where it goes?
Click a vehicle?
Yeah.
Yeah, you can, but it's not by clicking. You have to identify the vehicle ID first.
Oh, okay, yeah. You identified, yeah, some sort of.
So
yeah.
right here, for example.
Yeah.
Yeah, for example, actually you can, once you type a link, oops. Once you type a link ID, it will only show vehicle traversing through a specific link. And then, so you screen out only the vehicle traversing through a specific link. If we put a specific ID, a vehicle will actually show a flag, and you can follow that vehicle going through the system. So I can see as we are into an hour and 30 minutes, there are more queue builds up here, more queue builds up here.
Yeah, that's right, yeah.
Is that matching your reality there?
The reality is probably more congested.
Was the network preloaded with some initial values, or started from?
No, yeah, that's a good thing. I start from empty network, so that's why.
Well, that's why you see that, yeah.
Yeah.
It forms a little bit north of that, but since there's a lot of weaving and things going on up, so the queue usually forms a little bit north of that. Maybe it is forming, but I don't see it. But yeah, this is fairly good for an uncalibrated model.
You know, if you run 24-hour assignment, then the delay pattern will be more realistic because you have that traffic build-up from the early morning.
This is like a this point, right? Because
right, this is a peak hour demand, so I didn't preload. You know, ideally we want to have a warm up demand to start with.
That's right.
Well, I can see this is getting worse now. This area is
it is getting pretty bad now. Yeah, and it should get bad. Yeah, that's right. Oh, good. Yeah, this is very good. For the first trial, this is excellent.
Yeah. I had a lot of fun.
Network and a matrix. You didn't have anything else.
I have a lot of fun with this network. You know, in the last couple of weeks, we were just kind of playing and watching it, but we didn't do anything because we didn't really have time to do a lot of more calibration. Now the beauty of this model is I want to show you something. Maybe Robert, can I turn on another Data Studio? I can, right?
Yeah, you can do that. Use a Guam. Yeah.
I don't have a Guam actually.
The Portland Metro? Okay.
No, I want to do scenario comparison. So this is another.
Yeah, you have to use a Guam, and there's far more information there.
So this is not Portland Metro network. No, unfortunately, I don't have that. The only thing I have is I-70.
That's in Missouri, or I-70 in which state?
It's Colorado.
Oh, Colorado, okay.
It's from Denver to a famous ski resort area. This is Denver. And all the Aspen, Vail, Copper Mountain, they are in here. And what I want to show you here is just a scenario comparison where you can do for example, AnyMed system performance plot. And I'm comparing now. Okay, let me turn on to the baseline case here. I have a baseline case, so I set my default case is a baseline case. I I can do animated network plot. Okay, so I'm in the baseline case here. I can select a detour case, and then when I start to play it, you see plus minus value. So if the value,
okay, that's right. Yeah, you want to show values too? Okay.
later, I just want to show color first.
Okay.
So baseline, if baseline is higher, then it becomes red. It means that later on when you see red, it means traffic are diverting away from, and the green means that there are more volume in the scenario. That's where traffic diverted to. So this is too fast. Okay, so what does that tell us is that there's a diversion here because I'll show you here in the diversion scenario. So these are freeway corridor. These are I-70. They are going to have a construction and they are going to divert traffic. Construction on the tunnel is going to create a lot of congestion. So they want to know as a result how many traffic are started to divert to other route in the upstream. Just at this point, you can see that downstream volume drops. Plus means that baseline case has more volume than the scenario. So you can see that very clearly downstream of the construction, volume drops a lot. Not so much in the upstream, but it also implies that traffic started to divert to some other places. You can see the green here. Okay, so if I continue to play, maybe I can play a little bit faster.
Now, what does it have to do with the green earlier on the left side, close to Aspen?
Okay, so let's just look at this first for now. Okay, so basically give you a sense of diversion. Let me pause here. You can see that this is where construction is. And then so downstream traffic diverted means that throughout various points at the upstream, people started to take diversion route. And because that diversion, that construction is really, really bad. I mean, background information, this I-70 is already very bad. They want to solve the problem by expand the tunnel, but to do that they have to close the tunnel, so make the traffic even worse. And so you can see these are major diversion route people may be taking, and then maybe from here to divert to different areas. And you can see that this is where the bypass of that is, and traffic started, divert from other street. This is another town upstream of the tunnel, and the people started to find diversion from before they hit it, they got stuck in this construction area. So here, just want to kind of show you a very powerful way. There's another group using this tool to do a work zone analysis on I-96, in Michigan, to show they want to rebuild I-96, and then one of the scenarios is a complete freeway closure, and then they're very concerned about how far north and south of I-96 the traffic might be diverted to. And so they found this capability is fairly effective in showing the community how diversion might look like.
All right. Yeah. Very nice.
Robert, is there anything so basically this is the there's another feature. Let me see this one. I don't know if I can do it here. You can then compare scenarios. So this is one scenario, this is another scenario, detour scenario. If it doesn't tell much, maybe you can do is to set a background, delay information. You can use that to show color. You can see that this is a baseline case. The baseline case, and this is the detour. This is the construction scenario. You can see this situation is really, really bad. And there are additional diversion to other locations, and then the alternate route become congested too. And how this compare with the baseline case, and allow you to identify the new hotspot as a result of diversion. Okay, so this is just a way to compare both. Now I'm turning the background information on both sides, and you can have very quick visual on the comparison condition pattern. Okay.
All right.
So going back to our network. So Robert, is anything? I have to apologize. I probably have to leave about 10 minutes. So, Robert, is anything I kind of missed, or anybody any other questions?
Well, I think that you did a great job. I think that's yeah. If you give us more time, certainly we can put out more stuff. But you know, this is probably gave you the idea what the tool can do for you. Because my interest also in the future development plan is to do more integration work. For example, integrate DTA with a four-step model, integrate DTA with moves, those other more advanced analysis. So this is just the beginning of the development. Right now, basically just to able to run Dynasty and display the results. But in the future, there will be a lot more stuff to come.
Great. These are very encouraging. We'll be in touch with you soon to talk to you a little bit more.
All right. Yeah.
And this is impressive. Thanks, Robert, and thanks, Yi-Chang.
No problem. And then
we'll be working hard on this. Yeah.
And then Raj, and Raj, I'll send you and the mean will send you the video recording of our session today in case you want to review it again.
Sure. Yeah. That would be great.
Okay. All right.
All right. Thank you very much.
Thank you.
All right. You're welcome.
You have impressed us already.
Wonderful. Good to know.
Okay. We talk to you soon. Thank you.
All right. We'll be in touch. Okay. Bye.